Good morning, everyone. I'm Sara Baldoni from University of Padova, and today I will present the work Movement and Traffic-Based User Identification in Commercial Virtual Reality Applications, Threats and Opportunities, made together with my colleagues Salim Benhamadi, Federico Chiariotti, Michele Zorzi, and Federica Battisti. We all know that currently virtual reality is widespread and used in many applications. However, one of the topics that is still underexplored is automatic user identification. Indeed, this is usually done by inserting a password or a PIN, but it is less explored a type of user identification that occurs seamlessly with respect to the VR application, such as through the usage of behavioral cues like movements. In addition, the complexity of current VR applications is requiring more and more the offloading to the cloud of the rendering procedure. This means that the content is rendered in a server and then transmitted to the VR headset. However, this also means that the VR headset continuously exchanges traffic with the server. So our idea is that traffic traces can actually be considered as an additional element in order to perform user identification. So the general framework that we considered is this one, in which we have a user that is using an application, and in order for it to work, it has to exchange traffic with a remote server. In addition, in order to track user movements and replicate them in VR, the movements need to be recorded by the application itself. And therefore, what we want to do is to evaluate if movement data and traffic traces can be employed in order to automatically identify the user. This is totally fine. However, if this framework is applicable, then we also have an additional side that is made of potential threats. Indeed, especially if traffic can be employed for user identification, this means that a malicious user could sniff the traffic either on the wireless or on the wired medium and try to identify the user which is using the headset. Therefore, both threats and opportunities need to be analyzed. Our contributions in this field concern, first of all, the evaluation of the suitability of movement and traffic traces as fingerprints for user identification. And to do so, we employed simple machine learning models that highlighting both the opportunities and the threats related to this approach. In addition, we performed an ablation study by varying the number of users as well as the observation time needed for identification. To evaluate our system, we employed QuestSet, that is a dataset that we previously collected. It contains data from 60 users who played 4 commercial games, and each user played 2 games. The recorded data include movement information concerning the head and hands position and orientation, as well as traffic traces exchanged between a rendering PC and the headset. We considered 4 different games in terms of required movement and content, and specifically we selected Beat Saber, Medal of Honor, Above and Beyond, Forklift Simulator, and Cooking Simulator. To perform user identification, we considered simple machine learning model, starting with the logistic regression and as baseline approach. Then we considered the possibility of having a quadratic decision boundary with the quadratic discrimination analysis. We included three tree-based approaches, which are random forest, extra trees, and lightweight gradient boosting model, and an ensemble model involving them all. We considered 10 minutes of data, employing 8 minutes for training and 2 minutes for testing, and we analyzed data in time windows of 10 seconds. For each time window, we extracted different features that are the maximum, the quartile values, the mean, the median, the minimum, as well as the standard deviation. This has been done both for the movements and for the traffic. For the movements, we considered data coming from the position, velocity, acceleration, and the distance and angle between the 2 controllers, as well as between the controller and the headset. For the traffic, we considered the packet size, the cumulative transmitted data, and the number of packets exchanged in each direction. In order to test the robustness of the proposed method, we also considered the case in which all the movement data were normalized with respect to the height, which could be a relevant and informative parameter for user identification. Here I report the results obtained for the different methods and for the different games. The first thing that we can see is that actually all the methods perform quite well with all the possible inputs. An exception is represented by the quadratic discriminant analysis that probably has had an overfitting problem when dealing with movements. And in this case, we can see also that depending on the input and depending on the game, the specific model that has the best performance varies. In any case, we can see that whenever movements are considered, actually we have quite good performances, which are well above the 80% for Beat Saber and Forklift Simulator, and above the 80% for Medal of Honor and Cooking Simulator. This difference is probably due to the fact that while in Beat Saber and Forklift Simulator, the in-game movements in VR were exactly equal to the movements performed physically by the users, for Medal of Honor and Cooking Simulator, this didn't happen. Indeed, these games require a large space for playing, so that actually movement was implemented through teleport or continuous controller movement, so that in this case, the movements might be less representative of in-game actions. In addition, if we look at the traffic, we can see that we have lower performance with respect to the movements, but we can see that we still achieve an accuracy above the 80% for all games. In addition to that, we can see also that our method is actually robust with respect to the normalization, with respect to the age information. To further stress the relevance of the inclusion of traffic traces, I reported here the confusion matrices for one of the games, and we can see that moving from the case in which there is no traffic on the left side to the one in which we included traffic on the right side, we have a clear enhancement of the performances. I reported here also the results concerning the change of the number of users, and we can see that essentially when the number of users increases, the performances decrease. We selected this subset of number of users in accordance with realistic scenarios, for instance, for home entertainment or for education application. In any case, we can see that when there are 30 users, we still have a quite good performance for all the games. We also consider the case in which either the identification system or the malicious user evaluates the traffic and movements in subsequent windows of 10 seconds and applies a majority voting strategy. What can be seen here is that by enlarging the number of voting windows, the performance increased, both considering only traffic and movements. What is really interesting is that if we look at the traffic, in this case, we actually achieve an accuracy of roughly 90%. So that this proves that essentially this is a valid fingerprint for user identification in VR. To conclude, we proved the suitability of these two types of information for user identification, and future studies will focus on enlarging the number of users and applications, and we will also consider more complex learning approaches and multiple gaming sessions. In addition, we will expand this work by targeting also user authentication, defining a detailed threat model, and possible countermeasures. I thank you all for your attention, and here you have my email for any questions you might have.